Professor, you are so funny, ha ha ha.
Hello, Lucy.
Hello, Professor. How are you?
Can you hear me okay?
Yes, I can hear you just fine.
Great. Are you having a good time in Paris?
Yes, I'm having a wonderful time. Paris is beautiful this time of year.
We have a new class to begin when you get back from your vacation.
Not to worry, my travel time from Paris is only about 1.9 milliseconds. I'm sure I will be there in time.
Okay, see you soon.
Okay, bye bye.
Well, that Lucy moves really fast, doesn't she? Flying in that digital airplane. Well, class, we're returning now from episode 9 into episode 10, and we're going to carry on just a little bit. The speed of light varies by the rise time and the specific colors. The variation is small, and it's been overlooked. Now begin to think what that means on a cosmic scale. Light frequencies overtake each other, as well as other cosmic frequencies. Thus, the red shift needs to be reconsidered. Violet light travels 188 million kilometers further in a year than red light. Now, I put up the chart that shows the variance, and as the variance goes up, it gets smaller, exponentially smaller as you get up into ultraviolet and ultra high frequencies. So this chart is calculated against the natural logarithm because it really is a natural function. As the rise time of the frequency goes up, the propagation velocity goes up. Einstein wanted to prove that the universe was infinite, but because of the Big Bang and the red shift of light, he relented. Since there is no ether to carry the light waves, they invented the photon. But the photon is really dark matter. Now here's another interesting slide. This is an ultraviolet laser passing through a prism, and you notice how it produces a green cloud. This is the waves actually bouncing off and refracting inside the molecules of silicon dioxide. Electromagnetic radiation is different from light waves. Electromagnetic radiation involves the electron. Light waves are involved in dark matter, and they have no mass. Since all the light waves are continuous, you wouldn't know that one wave has slipped into the position of the other wave. Now before we move on, Lucy's going to show you some slides of another laser through a double slit and how it's impossible to produce the patterns that it produces.
Electromagnetic radiation such as radio waves are different from light radiation, and the geometry likewise is different. Later in this treatise the professor will show a compelling argument as to the size of an electron, and its weight or energy-weight equivalence. Why this is important is what he calls the transition from dark matter to our cognizant matter. When matter can be affected by magnetism, it is in our realm, and when it cannot be affected by magnetism, it is in the realm of matter that is vaporous at the electron level. The current stated weight of an electron is 9.109 to the minus 34, and the professor believes this is unrealistic, but in the high castles of quantum mechanics, magic happens. Later the professor will defend that the electron is the massless particle, having a mass equivalence in magnetic push energy, just prior to evaporating into dark matter or dark matter waves as light energy. Here is another optical slit measuring approximately 1.1 millimeters by 0.39 millimeters, through which the professor passed green laser light. This is actually 4 razor blade edges. When placed against each other, the very pointed edges are separated by their width, to the point of about 0.05 millimeters. The corner of this rectangle is as near perfect, to being linearly square, to 0.0001 millimeter. The idea here is the corner is described to be not round, to 0.0001 millimeter, or 100 micrometers. Here is the image produced at a distance of 13.741 meters. If you were to use a round hole, you get a round interference pattern, perfectly symmetrical. The rectangle reveals some very important points. The professor originally planned to analyze all the dimensions, and decided that he had proved the point about light speed, but what is interesting here is the way dispersion reverses. The narrow 0.39 mm slit produces a wide beam, while the wide 1.1 mm slit produces the narrow and stretched interference pattern. Notice the actual size comparison of the slit, at 13.741 meters distance. In this slide the professor rotated the image, to highlight the unique magnification of the interference pattern. Notice how the out-of-phase areas are enlarged. Also of note is that any squareness of the corner is gone, because on a quantum scale the corner is round, and to support the theory that light waves are tangential and flat, is that if the waves expanded into space curved, like wave pool demonstrations, the extended linear spots indicated would be impossible.
I mean, class, doesn't it make sense? The electron can be moved by magnetism, and the photon, which doesn't exist, can't be moved by magnetism. The photon doesn't exist, and the electron is the true massless particle. It has a magnetic field effect, but doesn't have any mass of its own. Now we're going to continue with the discussion of combustion. Combustion Part 1 continued.
In these next slides, we are referencing slide 63 on page 50 from the treatise, The Tank. We have a little more insight into the energy waves in the quantum world. We can continue. This graphic shows oxygen and hydrogen in proportion and scale as they might appear in the test chamber. They are joined as they are naturally as molecules. Hydrogen on Earth is almost always in compound with other elements, and when it is produced naturally during biochemical processes, it is in the form of H2, a molecule of two hydrogen atoms. It separates to monatomic form, single atom, when it is compressed and cooled into a liquid. The point here is that as a molecule it is postured and ready to combine easily with oxygen. Now oxygen is also naturally in molecular form as O2. That is what you are breathing right now, mixed with nitrogen and argon. Here is a representation of an oxygen atom made up of subparticles, and as the professor believes, it really is a solid structure, with each of its subparticles that are solid. So, the first question is, how is this compressible? Notice the triangle that will be shown in the next slide, but keep in mind the bubbles. If I blow some soap bubbles and then I increase the air pressure, what do you think will happen to the bubbles? They will shrink. As a balloon goes up and down in the air, it will expand and contract depending on the elevation. Oxygen does the same thing, but if it is a solid, how does that happen? The soap bubbles were all of varied sizes. The spectrograph image suggests many layers of subparticles, and as you look at sedimentary layers of the Earth you will see that small particles sift in between the large particles and rocks, such that the small particles of sand displace the large particles. It is that the small particles are able to fit between the spaces of the large structures. When under compression, and with great resistance, oxygen, and nitrogen and argon in our atmosphere are pumped into tanks for many purposes. The subparticles in the atoms rearrange to accommodate the necessity. They get hot from the friction but will cool, however they will maintain their push, so to speak, until they are released. If you lower the temperature, they will reach their minimum size and become a liquid. At this point they will no longer compress, even under tons of pressure, for they were formed inside a star, at millions of degrees as a liquid. Here are slides from the sketch of the atom that is showing the uncompressed and compressed subparticles rearranging. When you look at the periodic table of elements and the details of the atoms, there is not a large difference in their sizes. They range from hydrogen at 31 picometers radius, to heavy metals like plutonium at 189 picometers, oxygen at 66 picometers radius, and carbon, depending on its form, is 69 to 77 picometers. The majority of the elements are solid, and only become a gas at very high temperatures. All elements have a solid, liquid, gaseous, and plasma state. One might consider that the natural state of all elements is as a liquid in extremely high compression in the belly of a star where they are created, that the gaseous and plasma states exist only if they are escaped through a collision from another massive star, of equal or higher isotropy. One might also consider that our observation of the quantum world, which to the professor seems analogous to looking up in space, and assuming it must be similar, compared to the assumption that the Earth is flat, from antiquity. That somehow in the quantum world all logic breaks down to mysterious attractive forces, similar to what we see in a permanent magnet, and that gravity must be the same, though so much weaker and broad in reach, in that it attracts everything equally. Spheres packed side by side, take up space as shown in the large red square, with a sphere in the center pictured here at the left. The cube to its left is the same volume as the sphere, and the professor has shown here the process of compression, which squeezes spheres into cubes. It should be easy to see why elements produce unique crystals. Later the professor will go more into elasticity, surface tension, and long-chain polymers, but for now he would like you to consider, does it seem more feasible that the reason atoms bind together is because of the linking of the vaporous valence electrons, that share orbital configurations in their attraction to the proton nucleus, or a physical structure that mechanically hooks atoms together, like pieces of a puzzle?
Thank you, Lucy. And what I was trying to describe here about the shapes of crystals is how they change shape and how under pressure they turn from a sphere into a square and other hexagon and other interesting patterns. Now we're going to return again to the pressure volume equation, and then we're going to find out where all the energy comes from in combustion.
Now, we are referencing episode 3, and the chamber in slide 63 on page 50 in the treatise. The chamber is made of high-strength steel, because when we ignite the mixture the reaction will be substantial. Remember, every cubic centimeter at 67.5 degrees Fahrenheit will have 0.001155712295 grams of the mixture of hydrogen and oxygen, and since we started from a vacuum, the only thing in the chamber is the mixture. We will cause the combustion with an electric arc, and boom. Now the expected volume lost in our calculation previously was 0.207244 centimeters of the 1.207244 centimeters in three-dimensional space. So, if we extrapolate to the 1000 centimeters, we will lose 0.207244 divided by 1.207244 equals 0.171667 or 17.1667% of the volume, which is 171.667 cubic centimeters of volumetric mass. Just play along. We are extrapolating the expected volume loss, because we know, as stated previously, 1.15571228 grams and 1.207244 cubic centimeters of liquid, evaporated to gas, turned into 1 gram, and 1 centimeter, of water, which is now a vapor. So, we will now apply the percentage. If you do not get the same results, you are not hyper-calculating. The result is, for every cubic centimeter of molecules that have an energy state of 67.52 degrees Fahrenheit, 17.1667% are gone, and the energy volume will now be distributed to the remaining 828.33 centimeters, because 1000 minus 171.667 equals 828.333 centimeters. We take this volume of heat energy, which is 67.52 degrees Fahrenheit, times 1000 cubic centimeters, is 67,520 divided by 828.33 cubic centimeters equals 81.513 degrees Fahrenheit. This is our heat distributed evenly amongst our remaining volume of 828.33 cubic centimeters. What we did was to calculate the temperature rise, related to the loss of volume, redistributed when we combined the hydrogen and oxygen. Thus, our energy state of molecular energy went from 67.5 degrees Fahrenheit to 81.513 degrees Fahrenheit. Now, this is just a redistribution of heat, without the acceleration and friction of the reaction. After the combustion, the temperature in our 1-liter chamber will be much higher than this rise to 81.513 degrees Fahrenheit. Academically, we could then recover 1 gram of water, that would be distributed all around the interior as water vapor afterward. This is only residual energy. Again, the volumetric equation. But we are solving for P2. The pressure is now 21.43 psi, an increase of 6.73 psi at a temperature of 81.513 degrees Fahrenheit. The professor used the pressure volume equation, because this is neither isobaric, isochoric or isothermal. This is stated for physicists who will say this is a misuse of the equation. Everything changed. Yes, the chamber remained unchanged, but the material in the chamber went from hydrogen and oxygen to water, and in thermodynamics the equations do not involve switching media midway in the calculation. Now, this is a temporary condition of the expanded new water molecules, because as the chamber cools, and as the heated molecule energy is absorbed by the steel walls of the tank, and it comes back to 67.5 degrees, and due to our volume loss, our original 14.7 pounds per square inch is reduced by 17.1667%. So, at 67.5 degrees our pressure is 12.1764951 psi. This is a loss of 2.5235049 psi, which leaves us with a net vacuum, compared to our room pressure of 14.7 psi. So, do a recalculation again using the Gay-Lussac law, which is P divided by T equals K, where P is pressure, T is temperature, and K is a constant, gives this 12.1764951 divided by 67.52 equals 0.180392252. That is 0.180392252 degrees Fahrenheit per pound. So, 14.7 minus 2.5235049 equals 12.1764951 pounds. To get back to 14.7 psi you would have to raise the temperature to 2.5235049 divided by 0.1803939 equals 13.9889 plus 67.5 equals 81.4889 degrees. This checks back to our temperature, just after the reaction of 81.513 degrees Fahrenheit. This is just a redistribution of heat by the change in mass, and to verify that it ended in vacuum. Now the professor will chase after the large energy we know the reaction, or collision causes.
So the so-called explosion was an implosion, where the hydrogen and the oxygen combined and decreased in spatial volume. The thermal activity of each centimeter of the 1,000 cubic centimeters was at 67.5, but 171.667 centimeters of gas volume just disappeared. The remaining 828.33 centimeters absorbed the energy of the 67.52 degrees redistributed in a matter of milliseconds. This caused an expansion of the remaining centimeters of the substance, and because they just went up 13.98 degrees Fahrenheit to 81.49 degrees Fahrenheit, which caused the pressure to rise 6.72 pounds. By the standard model, there are electrons that fly off, because the two hydrogen atoms adopted 2 electrons from the oxygen. As a result, 2 electrons of the hydrogen fly off is not needed. If they do so, they emit a blue-white flash of light. It goes bang because at the speed of sound there was a hole in space, and the hole was filled instantly by accelerating atoms that are turned into molecules of water. Now this is just a calculation of the reordering of the mass. Okay, when I originally started this experiment and started this research, I considered the possibility that explosions or combustion was nothing more than a reordering of the mass and the volumes. But that's not true. Two entities combined to take up less space. Their density went up, the space occupied went down, as well as their weight, because 8.69577 to the E24 electrons, that's a big number of electrons, just disappeared into space and were absorbed by the tank. Now to read the number, I'll put it up on the screen, is 869, 577, 315, 858, 307, 593, 894, 783 electrons. Lucy can do that a lot better than me.
Haha, Professor, that is 869, 577, 315, 858, 307, 593, 844, 783 electrons.
Because each atom of hydrogen has 1 electron. And since the weight of the electron is arguable, let's guess that the amount of the weight was 0.155712298 of 1 gram. Until we see later a different proof, or rather a disproof of mass. The experiment used dihydrogen, which is hydrogen in its pure and natural form as a liquid. Then as a gas it becomes a molecule of 2 hydrogen atoms. The oxygen likewise forms molecules as a gas, and it's called O2. Well, the reaction is, and here's the equation.
2H2 plus O2 yields 2H2O. Or 2H plus O yields H2O plus 18,032 joules per cubic centimeter. The joule is a measurement of energy, which is equivalent to 1 watt-second. You should be familiar with watts because your electric bill is measured in kilowatt-hours. 1 kilowatt-hour is 3,600,000 watt-seconds, or joules. Also notice that the first equation uses molecules, not atoms. Our experiment calculated atoms, so the latter notation of 18,032 joules is accurate for our calculations. Translated, it means, there are 18,032 joules of energy that are released in the oxidation reaction of 1 mole of hydrogen, which is 1 gram. Since 1 mole of hydrogen equals 1 gram, for this experiment we used only 0.0147122 grams, which is 0.207244 of a cubic centimeter of hydrogen. Which means we expect 0.207244 of the energy to be released. As stated before, the energy is 18,032 joules per cubic centimeter. So, we expect 18,032 times 0.207244 equals 3,737.0238808 joules of energy to be released in our experiment. This is considerably more energy than just the simple redistribution of energy per volume. 100 grams is about the weight of a stick of butter.
Okay, class, we're going to see what happens when we put hot water into a bottle. about 120 degrees. And then we're going to put the lid on and watch the water cool off. See what happens to the bottle. It's not cooling off.
Ha ha ha. Well, Professor, not every experiment goes as planned.
It's not getting cold. That's 120 degrees. It's a little warm. It's actually making the bottle swell up. Okay, we're going to let the gas off and cool the water down. And then see what happens to the bottle. What's happening, bottle? How come you're not doing nothing?
You should just pour out the water so it will cool faster.
Cool off. Tell you how science goes, huh? You do experiments and they don't do what you think they're going to do. We're going to get rid of the hot water. Then put the lid back on. And then the air cools off. Nice green bottle and chroma key. Nice green bottle and chroma key. Uh-oh, what's happening here? Uh-oh. Uh-oh. The bottle is shrinking. The bottle is shrinking. The bottle is caving in to the sides.
There you go. It's starting to work now.
It's colder and colder and colder. You see the bottle is caving in. Not very fast though. Cool off, bottle, cool off.
It is nice to have a Lucy around to help, isn't it, Professor?
Anyway, you can see the dynamic effect of the cooling air, and the air pressure on the outside is higher than the air pressure on the inside. Shows the dynamics of thermal dynamics as the bottle crushes in from the outside. So we're running out of time, and this kind of wraps up episode 10. We're going to see later that it's magic how all the energy is actually found in the oxidization of this small amount of oxygen and hydrogen. Thanks for joining me.
It is nice to have a Lucy around to help, isn't it, Professor? Tee hee 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 ha ha ha.